Welcome to my talk. This is a talk about a very elementary result, that implementing controlled unitary, given the unitary as a black box, is impossible. It's joint work with Matan, Seidel and Yonathan, Touati. Our impossibility of controlled unknown unitary follows from a topological lemma. I will show the reduction to this lemma, and then I will prove the topological lemma itself. It only needs basic algebraic topology, such as the fundamental group of the circle. A corollary of our result is a separation between two seemingly equivalent models of computation. The problem can be formulated very simply. Given a d-dimensional unitary as a black box, implement control of U, which is controlled U, i.e. an operator which implements the black box if and only if the control is 1. So here I formulate this as a function from unitaries to linear operators. On the task Hilbert space, I call this the task function, and the task Hilbert space in this case is the tensor product of the control qubit and the target qudit. One suggestion to implement control U is to use a Mach-Zehnder interferometer. This is an optics experiment in which we choose the polarization degree of freedom of the photon to be the control, and then using polarizing beam splitters, we couple this degree of freedom to the path degree of freedom. So, for example, we send horizontally polarized light through path A and vertically polarized light through path B. And the entire scheme implements the linear operator that we wanted, controlled U. But it is actually not truly black box, because we know something about the oracle, namely its location. So we are promised that on all states that have on their first Hilbert space state A, path state A, the oracle acts as an identity. So they are the +1 eigenstates of the oracle. Actually, implementing controlled U in a truly black box way is impossible. This was observed by Araujo and others, and Thompson and others, because assume that we can implement control U from U, then take for U either identity or the minus identity. Then you will actually implement identity on the control tensor, identity on the target in the first case, and Pauli Z tensor identity on the target if in the minus identity case. And these two implemented operators are perfectly distinguishable. So we managed to perfectly distinguish what should be physically indistinguishable. That's the contradiction. We need to relax our task function, so we will change it from control to control phi, where on input U, control phi of U is a linear operator which implements controlled U up to phase phi. And this is a relaxation of the problem, because we are interested in implementing control phi of U for any real function phi. About this problem, Araujo and others concluded that it is impossible from one call to the oracle U by a unitary circuit, because any such circuit with only one query takes this form, where V0 and V1 are fixed unitary operators, and the entire implemented operator A of U is just a multiplication of gates, and because we have only one call there, it is linear in U. Then they use linearity arguments to show that no such phi exists, such that control phi of U could be implemented for all U. But we are actually interested in allowing also multiple queries to U. Then an idea when allowed multiple queries to the oracle is just to do process tomography on the oracle, which is sort of a brute force approach, and get out a matrix that approximates U and then to decompose this matrix to elementary gates, add control to each one, and implement this to the task Hilbert space. We will see that this approach actually cannot implement control phi of u for all u. What we can do is to implement control phi of u if we are given queries to fractions of u. Namely, Dong and others have shown a unitary algorithm that can do this. This can be represented without loss of generality by this diagram, where sigma I are what I call query functions from the unitaries to linear operators on some matching Hilbert space, and the query functions in case of the algorithm of Dong et al. Are fractional powers. We, however, want to allow only queries to u and u dagger, so our query functions will be the identity and the inverse. It might seem strange that I use operator functions to represent everything, also what we want to implement, and also the queries, but this is actually crucial to getting to our result. So we've seen so far two kinds of operator functions, those that we want to implement, which are called task function, and those that we are allowed to assume, which are called query functions, and they are collected in query alphabet. Then to fully characterize a problem that we want to solve, we need both the task function and the query alphabet, and I will call the pair task. Then the task that we are interested in has identity and inverse in the query alphabet, and the task solved by Dong and others has the same task function but fractional powers in the query alphabet. But note that the algorithm that they show actually uses only one type of fractional power, multiple calls, but to only one fractional power, that is 1 over d, where d is the dimension of the unitary. So they only use queries to d fruits of u. If in their algorithm we replace these simply by queries to u, or this function by the identity function in the language of functions, then that algorithm will implement control u to the d. And so this is also possible by the same algorithm. Compared to our question, we define a family of tasks that I call CUM, that the task function are control u to the m up to phase, and for m being any integer. And our result is actually about this family of tasks. Next, I want to define the model in which we want to achieve a task. Note that the algorithm of Dong et al. Is inside this model. So we allow for any finite number of queries from the query alphabet. In particular, n can be any function of d. And our algorithm is unitary, followed by a binary success-fail measurement, and we only care what happens or what is implemented in the success case. In other words, we allow for post-selection. And without loss of generality, we can represent this by just inserting projection onto the success into the circuit. And note that then the output is going to be, doesn't have to be normalized. We will absorb this factor into the ancilla so that the task output remains normalized. Then the probability of success is equal to norm squared of the ancilla output. And I impose that this is non-zero for all unitaries. This is consistent with the definition of post-selection, and it makes sure that our model is worst case. And again, we will use another operator function to represent each such algorithm. It's a function from unitaries, from oracles, to linear operators on the large Hilbert space. And we say that an algorithm achieves a task if when ancilla is initialized properly it implements the task operator to the task Hilbert space. And we also allow for approximate implementation. So we defined a very strong model, which also allows for postselection and is happy with only approximate implementation. This will make our impossibility strong. Then our main result is the dichotomy theorem. It's about the family of tasks CUM, and is the following. Let D be the dimension of the oracle, M an integer, and epsilon smaller than half. If D divides M, then CUM is epsilon approximable. If D does not divide M, then CUM is not epsilon approximable. So the positive direction follows easily from the algorithm of Dong and others. The negative direction is our main contribution. And note that for n equal to 1, we get back our original question of control due. And this implies that it's impossible for any non-trivial dimension. To prove this impossibility, we will need the following topological lemma. Let D be a natural number, M an integer, a continuous M homogeneous function from the D-dimensional unitaries to the circle exists if and only if D divides M. And a function f is M homogeneous if this equation holds for all scalar lambdas, which in the case of unitaries must be on the circle. And an example is the determinant, which is D homogeneous. We will prove the theorem given the topological lemma by assuming an algorithm that achieves CUM and reducing it to a function of the lemma. So any algorithm, when seen as a function, operator function, can also be continuous and homogeneous, the two properties that are in the lemma. This depends only on the query alphabet. Because we can write A of U, the implemented operator by the algorithm, as a multiplication of gates. And then if each query is continuous, so all the query functions inside the query alphabet are continuous, then A is continuous because it's just a multiplication of continuous functions. And the same goes for homogeneity. And also note that continuity is the case for identity and inverse, and also homogeneity. Identity is one homogeneous by this definition, and the inverse is minus one homogeneous. And since A of U is just a multiplication of them, A is going to be W homogeneous, where W is just the number of identity queries minus the number of inverse queries. So we said that RA for our oracle alphabet must be continuous W homogeneous for some W. Next, but we also assume that it achieves the task. So it implements the task operator T of U when the ancilla is properly initialized. And our task operator is indeed control U to the M up to phase. And I am only proving the exact case here. Epsilon equal to 0. Now from this algorithm, we will build a new circuit which acts on task Hilbert space and ancilla Hilbert space. And the task Hilbert space I split to the control and the target. And the circuit itself contains Pauli X flips of the control. And at some point, there is a projection onto the all zero state of the ancilla. And I claim that the output of this circuit is actually the all zero state rescaled by the norm squared of G of U. This is due to the projection and the fact that G is the output on the ancilla. and by the phase e to the minus I phi of u, which comes from a dagger being applied when the control is 1. And also note that the circuit, when seen as a function on operators, is continuous because all of its constituents are continuous. And A is W homogeneous, A dagger is minus W homogeneous, and U to the M is M homogeneous, so C is M homogeneous. So if we build the following function, note that it is well defined because the denominator is just the probability of success, which I said must be non-zero, and it is actually equal to the norm squared of G of U. So if we substitute the output of this circuit, then we get that f of u is actually equal to e to the minus I phi of u. So it's a function from the unitaries to the circle. And it is composed of continuous functions, so it's also continuous. And C was M homogeneous. The denominator is 0 homogeneous, so F is M homogeneous. Then from the lemma, we get that D divides M. So we only assumed that there exists an algorithm for CUM, and we got out that the D must divide M, which proves the impossibility. Next, I will prove the topological lemma, but first I note that the case of even D and odd M can be proven via Borsuk-Ulam theorem. But here I want to show the general direct proof. So we will look at paths on the space of D-dimensional unitaries, and we will parameterize the paths by T. And so the starting point is u of 0 and the ending point is u of 1. And we will also need the concept of homotopy. Two paths are homotopic if they can be continuously deformed to each other. So we define the following unitary paths. When you look at the first path, note that the factor here is actually a loop on the circle. Starting at 1, this is the complex plane and making one loop. So the unitary path is the diagonal entries of the matrix simultaneously looping on the circle. The second path is the diagonal entries of the matrix looping on the circle one after the other. So this is the jth entry, and we are looking at the time interval between j over d and j plus 1 over d, so delta is between 0 and 1, and then the jth entry is making a full loop. I claim that u and u primed are continuously deformable to each other or homotopic. And then we have the third path, which is making d loops only on the first entry. And I claim that making one loop on each in sequence and d of them on the first is homotopic. Both of these homotopies are simple to show, but see the paper for them. And note also that u prime primed is a periodic function. Each interval behaves on each interval it behaves exactly the same, and inside the entire 0-1 interval it makes d periods. And by transitivity, we wanted to get that this path is homotopic to the path u. Now assume a function from the unitaries to the circle, which is continuous M homogeneous, and compose it onto these two paths. Then, since this function is continuous, we will get two homotopic paths on the circle. The composed path must be homotopic. And from the M homogeneity of F, if we substitute for u of t, we get that this is equal to e to the I 2 pi mt f of identity, which corresponds, it's on the circle, it corresponds to starting at some point f of identity and making m loops on the circle. M loops for this composed path. And note that u primed primed had d periods, so the composed path is also going to have d periods. And if on each this interval on the circle it makes k loops, then in the entire 0, 1 interval it will make kd loops. Now, different numbers of loops on the circle cannot be homotopic. This is just another way to say that the fundamental group of the circle is Z generated by one element. So this must be the same in order to be homotopic. We must have that M is equal to KD, or that D divides M, which completes the proof. We have seen that control phi of U for all U is impossible, even with postselection and even approximately. In particular, it is impossible by process tomography. So what is it then that the process tomography strategy does? Process tomography can approximate control phi x of U, where x is drawn at random from some index set of success measurement outcomes, and the set must be at least of size 2. This is because we cannot drop the x dependence, remaining also worst case, so working for all U, because we cannot rotate continuously phi x to some canonical phase phi. This is a simple corollary of our lemma. Therefore, if we are happy with implementing control phi x of U, where we know phi x, but we get it at random, then the process tomography strategy can do this. And note that our post-selection Oracle algorithm model cannot do this because it has only one success outcome. So the x parameterized problem is the same as the x independent problem, which is impossible. Summarized in a table, the algorithm which has binary success fail measurement sees the two problems as identical as impossible, and algorithms which have multiple outcomes and many of them are considered success see the two problems as different, and the second one, the randomized one, is possible. And an example is this process tomography strategy. Therefore, if we are happy to implement, if we are solving a problem where multiple outcomes are considered correct, and we are happy to get one of them at random, then it could be truly advantageous to try to develop algorithms of the second model. One example of a new algorithm could be an algorithm that does control phi x efficiently, because process tomography doesn't. But I would be very interested to find other problems that see the difference between the two models. Welcome to my talk.
Okay, so thanks, Zuzana, for the talk, for a very nice talk. Zuzana actually is now with us, so she can answer questions or comments. So I encourage you to ask them via Slack. Before they appear, I ask some questions. Yeah, welcome, Zuzana, first of all. So if I understood well, your no-go theorem, when you allow for post-selection, somehow assumes that this post-selection probability is always non-zero.
Yes.
So, like, what if sometimes you get actually, that for some instances you get zero success probability?
So actually, in that case, I mentioned this result of Dong and others that implements controlled unitary from fractional queries. So we have an algorithm that can do this. And there exists another algorithm due to Sheridan, Maslow, and Mosca, that is average case, that for most unitaries can do fractional powers. So combining the two results, we will get average case control phi of u. So this is possible. So I only asked in the.
I mean, but what I meant, you showed that sometimes it's impossible, as far as I like if you can query not in a fractional manner, but if you can query just u, then you gave this beautiful topological proof that it's impossible. But as far as I understood, in the way, because you reduce it to those, you reduce the quantum protocol to you infer from it existence of a homogeneous function, and I guess you need this to assume that the success probability doesn't vanish there.
Yes.
Maybe. So I'm asking about this, like, do you think it's going to, like, what if for some inputs it vanishes, the success probability?
Okay, I see. So you're asking where the proof would fail. So it would actually, the impossibility proof would fail. Let me find the proof. So when I do the reduction, when I do the reduction to the function that is to the circle, it will actually so there is a reduction. So I reduce this to a function that is from the unitaries to the circle, and it can be easily extended to approximate, by the way, because we can just extend the margin and the topological proof works as long as we exclude zero. But what you're asking is that if we actually include zero, then this is going to be topologically very different space. So if the probability can be zero for some unitaries, then we sort of get a different topological space in reduction.
Sure. Let me just quickly comment that so it might lead to some nice mathematics, because then you will have like a not fully defined maps, like it will go to algebraic geometry a bit. It feels like it. Let me move to questions by the audience. So I think we have time for one question. So Claire, Christian Song, if I pronounce his name well, asks. Right, so if I try to rephrase, because I had actually a similar question. So the unitary, as it is defined up to a global phase. So it's not a unitary channel is defined up to. It's not defined uniquely by you, right? So does it make sense to phrase the problem in this way, namely allow dependence on you, namely the unitary, not the element of a projective unitary group?
So I'm not sure if it refers what I said at the beginning, that it's impossible to do control U if I do not allow this freedom in global phase. I'm not sure if this answers the question. But actually in the reduction also, for example, in the process tomography, so the process tomography can access the superoperator, which is a unitary superoperator, and it's not sensitive to the global phase. But then, so say like some curly U, but then we actually need to choose some unitary such that the curly, such that this is true. And we need to make a choice because we want to implement control of U, which is sensitive to the global phase. Like it's a different, like it makes a difference which one.
Sure, of course.
Which choice I make. So actually, this impossibility has something to do with that it's called section, that this cannot be continuous choice.
Right. Okay, thanks. I guess the time for questions is over. There are still some left on Slack, but okay, but thanks again. So now Zuzana, as the other speakers, would go to the round tables to separate Zoom rooms. So we are encouraged to join the speakers there. Let me thank again all the speakers of this session. Yeah, and enjoy the rest of the conference. Thanks again, Zuzana.
Thank
Yeah.
you.